Good morning, everyone. Welcome to today's seminar. Today we have an in-house speaker, Pierre Guillard. So most of you know, of course, Pierre, and he did his PhD a long time ago at
Same
EIS.
year as you, I think.
Same. At EIS with François Boulanger and Guillaume Pinot-Desforêts on H2. Same topic, so he knows what he's talking about. And then he did a postdoc at Caltech from 2009 to 2012. And then he got a CNES fellowship at EIS as well, before getting to IAP as an assistant professor at Sorbonne Université. And he was also a member of EUF. And Denis, who was asking about you, this is Pierre Guillard. So
Hello.
not everyone knows you, apparently. So yes, he's going to tell us about JWST because he's involved in the MIRI instrument, characterization of the PSF, and the GTO time with MIRI for the ISM studies, but also in Euclid. He works also in Euclid for the VIS instrument and the PSF as well. So today is going to tell us about H2 molecular gas with JWST. Thanks, Pierre.
Thanks, Hakim, for the nice introduction. It's a pleasure to talk. I think the last time I talked here was pre-launch of James Webb, and I'll try to show you that the physics that we're learning, physics of the molecular gas, so the gas that is forming stars, is evolving quite fast with James Webb, especially with the ability to actually characterize at very high spatial resolution the impact of the kinetic energy input from AGNs from stars into the molecular gas, so what we call feedback in astrophysics. This is not working. That was working before. Of course, maybe I need to click. Yeah, I need to click on it. But first of all, I'll give you a brief introduction of why we are interested in H2, the most abundant molecule of the universe. But H2 is, you will see a unique tracer of the dissipative processes in the interstellar medium. So the way the radiative and mechanical energy is reprocessed into the ISM, well, H2 is a very good tracer of those processes, very complementary to the carbon monoxide molecule, the CO molecule that we are commonly observing in galaxies, but that molecule traces the cold gas, the gas associated with the star formation, the gas that has already cooled down, and H2 is tracing the way gas cools, and that's a very interesting process because it traces the energetics of the gas rather than tracing the mass of it, and it's a very efficient gas coolant also, so James Webb is really opening a new perspective. James Webb will observe H2 in thousands of galaxies. We had only a few dozens of galaxies before with Spitzer, the previous generation instrument. So it's really changing the game here. And rather than drowning you under new results and doing a catalog of results, I'll focus on a few of them. One related with star formation, the pre-phases of star formation, what we call the protostellar outflows. And the second one is related to galaxy merging and AGNs. So let's say active phases of galaxy evolution, the phases that inject the kinetic energy into the gas. And if I have time at the end, I'll show you how what we can do with those thousands of hundreds of lines that we're observing now in galaxies, in thousands of galaxies. So what do we do with them? And I'll try to show you that, well, molecules, they are really a challenging provenance. They allow us to trace the processes related to the dissipation of mechanical energy, but they're also very challenging challenging to model. And we've attempted at doing, let's say, a toy model to actually use those lines to try to quantify the radiative and mechanical energy budgets of galaxies, something that is really sometimes when we fit lines, we put that under the carpet. And so we'll try to do that today. So why is mechanical energy dissipation important? Why is turbulent important? Well, I take here the example of galaxy formation, but I could have taken another example. This is related to what a lot of people do here at IAP. Turbulent is ejecting on large scales through accretion, gravitational accretion, and feedback processes from the stars. And so, in fact, what is important is that galaxy formation, it's really a competition between accretion, feedback processes, and star formation, which consumes gas within galaxies. In fact, during early phases of galaxy formation, the potential energy of this gravitational collapse dominates the total input, energy input from young stars, both the radiative and the mechanical energy. So it's an important process, and this energy, this gravitational energy, the mechanical energy associated with the gravitational collapse and the feedback has to be dissipated. The gas has to cool down for stars to form, because you need to cool the gas first before forming stars. In fact, what the simulations tells us, and also X-ray observations of, let's say, clusters, for instance, is that part of this mechanical energy goes into outflows. So you eject part of the mechanical energy out of the system. Another part is being thermalized, and this is what most people actually study here, is that the gas is virialized, and the gas is shock heated at the virial radius. And let's say it's kind of a sterilization of the gas. This gas has a very long cooling time scale, so you don't form stars out of this gas. And another part of the kinetic energy has to cascade down to very small scales where it is dissipated. And we don't really know how it's done, but we know that this turbulent reservoir is there because we observe H2, we observe large reservoir of turbulent gas in galaxies. So this is really an open question. I mean, is turbulence, is accretion, turbulence driven by accretion and feedback, key processes to actually regulate the gas content of the galaxies? This is what drives the properties of the galaxies we observe today. It's an open question we're trying to address here through local examples, and now James Webb is starting to open the way to observe those lines at very in the early universe. So I think the key question here, that this is really the key question I will address through this talk, is how does the gas cool, and in which phase of the gas the mechanical energy is dissipated? This is an open question. We really don't know that. What I mean by phase is whether the phase of the gas is molecular, cold and molecular, or ionized or atomic. Those are the different phases of the ISM. So can we find observational signatures of this dissipation of turbulence? The first one, I think, is related to the shape, the morphological structures we see in ISMs of galaxies, so interstellar medium of galaxies. If I show you an image like that, unless you really know the structure, it's very hard to put a physical scale, okay? Whether it is a local image of the ISM in our galaxy, whether it's ISM in an external galaxy, you cannot really tell. In fact, this is the Large Magellanic Cloud. But what is remarkable is that those structures, filaments, clumps, they are scale invariant. And this is a property, this is one of the manifestations of the way turbulent energy is dissipated into the ISM. If I zoom in, or even if I look at the pillars of creation in our galaxy, you have the same kind of morphological structures at all scales. And this is what we call the scale invariance. This is really related to the way energy is dissipated. I was telling you, in fact, this is really related to the what we call the intermittency, the fact that the kinetic energy is dissipated locally in time and space. You don't dissipate energy at all the scales. It dissipates very locally. It's associated with the high vorticity structures in the ISM, and many observations have shown that in the local, in the ISM of our galaxy. The way we represent this cascade of energy from large-scale injection, so this is a power spectrum of the energy in the ISM as a function of the inverse of the scale. This is the large scales on the left at which you inject the kinetic energy. This can be done by star formation, supernova explosions, AGN feedback, jet-driven, AGN jet-driven, for instance. And then this energy has to cascade to small scales where you reach what we call the dissipation scale at which the energy is dissipated. And the dissipation forces associated with these processes are multiple. It can be friction, it can be compression. This is the way you actually force turbulence in the system, whether you drive more like solenoidal forcing, meaning you really stir the gas, or whether you compress it by shocks. And two fundamental processes, ambipolar diffusion and magnetic diffusion, those are fundamental processes because those are the ambipolar diffusion scale, the decoupling between the ions and the neutral in the gas. This is the scale where you actually start to heat the gas and excite endothermic reaction, for instance, in the molecular gas. So you start to activate some chemical reactions. And this is where the energy dissipates through emission lines, and H2 is a good tracer of that. This is why I told you that molecules are really a providence at probing those scales, because this is at those scales, very small ones, hundreds of AUs in the diffuse gas of our galaxy, 0.1 parsec, let's say, for more dense gas, shocked dense gas in the cloud. So very small, I'm talking about very small scales here. This is just to remind you that you cannot neglect turbulence. Those are the different average heating rates in the ISM of our galaxy. And you see that whether the energy is reprocessed by UV photons, cosmic rays, magnetic flux, the ambipolar diffusion is also a way to redistribute the magnetic flux in the gas, and turbulence, well, all of them are, let's say, comparable in orders of magnitudes. So you cannot neglect one of them. And we've been using different models depending on the different environments, whether you're dominated by UV reprocessing in galaxies, or whether you're dominated by shocks or by turbulent dissipation regions. So this is models linked to how the vortices are put in the system. So why H2? Well, as I told you, here I'm comparing how we basically observe the molecular gas in galaxies. This is the cold molecular gas is traced by the CO molecule. As you see here, I'm showing the first rotational levels. So levels related to the rotation of the carbon and the oxygen bound. And so you see that the temperatures associated with those levels, they're very low. So it really traces the cold gas. Whether the molecular hydrogen, it's those rotational levels, they're high, so they trace really the warm gas, the energetics. You need to have gas, let's say, at temperatures above hundreds of Ks to start to populate those levels. So on the left, this is very easy to do. We've been doing that for many, many years with radio telescopes on the ground. On the right, it's very challenging. You need to go to space to observe those transitions because they radiate in the mid-infrared. mid-infrared are those rotational lines, so rotation of the two hydrogens, and it's radiating in the mid-IR, so you need to go into space. In the near-IR, you have raw vibration lines, raw vibration levels that you can observe from the ground, but it's very challenging. VLT, for instance, has been doing that in the near-IR, but now you will see that with James Webb it's very easy. Gas H2 is, well, here I'm putting again the first rotational levels because you will hear that in the rest of the talk. So the pure rotational lines from 28 micron to 5 microns, so really radiating, let's say, in the range where the MIRI instrument on board James Webb is observing, and the raw vibration transitions in the near IR where the near spec instrument on board James Webb is observing. And you have many ways, I won't enter into the details, but you have many ways to excite those different levels of energy of H2, which traces both the collisions, the formation of the gas onto the grains, and the UV excitation of the molecule. H2, you cannot avoid to go through H2 lines when you cool gas from the warm ionized medium. So let's say gas at 10 to the 4 K. When this gas, which can be excited by shocks, it can be UV heated gas in galaxies. When you want to cool the gas to the right to temperatures of the cold molecular gas, when you can start to have collapse and form stars, you go through those lines, S2, S1, S3. Those are the mid-IR lines that are observed with James Webb. Those are the dominant lines that trace this cooling gas as a function of the density. So you see that it's really bridging the H2 emission. It's really bridging the warm ionized phase to the cold phase. It's both ways because you can go from cold to ionized gas, for instance, if you UV heat or if you shock the gas, but you go through those H2 lines. So really fundamental processes. In terms of astrophysics, H2 has a lot of importance. I won't detail all of that in the rest of the talks. It's not a review, so I will be very biased here. But it's the fuel for star formation. There is a very good correlation between the infrared luminosity in galaxies. So in fact, the UV reprocessed emission through dust grains that radiate in the infrared and the H2. So you can use H2 to trace star formation. It actually influences the formation of the cosmological structures because as soon as you form H2, you affect greatly the cooling of the gas and the cooling of those first objects, like population-free stars, but also cooling of gas in filaments. It affects planet formations. In fact, the circumstellar disks in which planets are formed are made of 99% of H2 in mass. So, and H2 controls the cooling of those disks and their thermodynamics. And H2 is the start of molecular complexity. It's really the molecule where you can start the whole chain of chemical reactions. As I was saying, I'm just showing an example here. The thing to remember is that in star-forming galaxies, so let's say classical galaxies that are on the main sequence, there is a correlation between the total H2 luminosity. So this is the luminosity of the rotational lines, of the first rotational lines of H2 as a function of the emission of the dust, the infrared emission of the dust, here traced by the PHEs. Those are aromatic molecules that we observed in galaxies, and you see that there's a very good correlation. And already you see that there is a good correlation for star-forming galaxies, dwarfs. Those are the diamonds here. But you see that for AGNs, for active galaxies, already Hélène Roussel here had shown that there is a little excess of H2 emission for those galaxies. So something is heating the gas. There's some kind of extra heating of the gas, whether it is shocks, whether it is cosmic rays. Really, James Webb is trying to address those questions precisely, but you see that there's some extra heating. And the bottom line is that in star-forming galaxies, most of the H2 emission is coming from photodissociation regions, so interaction of UV to UV cloud interactions, and we can use photodissociation models to fit the different levels of H2. This is what I'm showing on the right. This is the different column density of the H2 levels, and the models in red fit extremely well the observations which are in black. Okay. So we know that on average in galaxies, H2 emission is mostly coming from UV pumping. So James Webb, this is the sensitivity of James Webb instruments. I'm putting that here to actually highlight the fact that we are gaining 2 to 3 orders of magnitude in sensitivity and spatial resolution compared to previous instruments to observe H2. Okay. In the mid-infrared, where the rotational lines are shining, you see that the MIRI instrument is 2 orders of magnitude, has a 2 orders of magnitude better sensitivity. So H2 tracer of dissipation of turbulence, what's a nice example is shown on that image. It is a spectacular image of a protostellar object. This is a R big arrow objects. So this is actually those we are looking at here at the first phases of the star of formation of star. Here at the center, there is a baby sun. There is a star that is a few tens of thousands of years. So 8% of the age of our sun, which is it's buried in dust, so you actually cannot see the star because there is some dust obscuration. But you see the manifestation of the process of star formation because of conservation of angular momentum. When the gas is collapsing to form the star, you eject gas in those forms of spectacular outflows. This is a very important phase of star formation because this is the phase where most of the mass of the star is gathered, but also the phase where most of the gas is expelled. Actually, this is the phase where you have maximum accretion and outflow rates. And H2, because what you are looking at here is almost a pure H2 image. Okay, and I will show you that why in a minute. This is not dust. Emission. This is not, this is almost pure molecular because H2 is shining because of the dissipation of the mechanical energy. And why I'm saying, so it's a composite, you see that this image is a composite of many filters from 1.6 micron to 4.7 microns. Why I'm saying that this is pure H2? Well, this is because we took a spectrum with NIRSPEC, spectrum at the tip of the bow shocks that you see here. And this is what the spectrum looks like. It's almost a pure H2 spectrum. All of the lines that you see here, all of the vertical lines, they're rotational and row vibration lines of H2. You see, this is almost, it almost looks like a lab spectrum. This is very spectacular. There's a lot of physics to do. It's going to take years to actually model and interpret those kind of spectrum. But you see that there is this is not continuum subtracted. So there is a very little dust emission, very little continuum, but pure H2. There's H2, but not only H2, there's also CO. All of those branches that you see here are also the R branch and the P branch of the CO for the experts. So this is a NIRSPEC spectrum taken at the tip of the bow shocks here. We've mapped those outflows with the MIRI instrument on board James Webb. So we did a map of the southern part of the outflow. Here I'm putting the same image, and you see that the filters of NIRCam, of the near-infrared camera, they're dominated by some of the lines. So the image that you saw is a pure H2 image. We've mapped that now to trace the rotational transition of H2 to have the bulk of the warm molecular gas in the outflow. And what you see here on the right are MIRI maps. So this is a MIRI of the transition at 10 micron, 9.7 micron. And you see that it's very bright. There's a cocoon of molecular hydrogen gas, but it's very bright at the tip. So actually the luminosity of the H2 is not decreasing with distance, as you might expect if you had UV excitation. It's the opposite. The temperature is actually increasing when you move away from the source. So when you go from the jet to the bow shocks I was talking previously, those bow shock structures that you see at the tip. So we can construct from the studies of the rotational lines, we can construct maps of the temperature, and you see that the temperature is higher when the shocks are actually hitting the parent cloud. The velocity decreases from as the jet shocks the ISM and it excites those H2 lines. So we can do a lot of physics of how the flow is driven, and this has a very strong impact on the models of how stars feed back energy to the system, not only radiatively, but mechanically, and this is a key ingredient for the evolution of the gas in galaxies. Okay. How do we know that it's coming from shocks? Well, we use models, and people at LP, at the laboratoire of ENS are really specialists of that. So we've been using their models to interpret. This is a 1D MHD model of a shock driven into a molecular gas. So you see the cooling. You see the cooling in the y-axis and the shock velocity on the right from 5 to 40 kilometers per second. And the bottom line is that H2 in blue, this is the curve here. H2 is really dominating the cooling. This is the main coolant in those shocks. Okay. You see that the magnetic flux energy is important because this is those are the pre-shock gas. The pre-shock gas is magnetized, and because of the unpopular diffusion I was talking about before, you redistribute the magnetic flux, and which is a significant part of the kinetic energy of the shock is actually redistributed in the magnetic energy. So shock triggers the emission of H2 in those systems. From those models, we can predict, we can use those models to predict the spectra we can observe with James Webb. So those are different spectra from in the James Webb wavelength range. You see the near spec range here in the near infrared and the MIRI in the mid infrared. For different shock velocities. This is just to give you a flavor on how we interpret those H2 lines and how the shock velocity actually impact the spectra. You see that at very low shock velocities, you weakly heat the gas, so you mostly excite the pure rotational transition of H2, the first levels of H2, and as you go higher in velocities, you start to excite those forests of lines. So those forests of lines are color-coded by their vibrational levels. So as you go from 0 to 6, you go higher and higher in vibrational levels, and you start to excite those forests of lines. Shocks are not only the only powering source for those lines. When you increase also the radiation field, so this is the main UV, this is the average radiation field in unit of the average radiation field in our galaxy. So G naught of 1 is the average radiation field in our galaxy. And you see that if you go from standard radiation field to very high radiation field, for instance, if you're close to star-forming regions, you start also to excite those forests of raw vibrational lines. And you can use those models to actually derive the physical conditions. What about galaxies now? So what is, I think, a game changer with James Webb is that we can do the very detailed studies that we were able to do with Spitzer in the very local ISM, in the ISM of our own galaxy. We can now extend those studies to external galaxies. And so really James Webb enables to image the morphological structures of the interstellar medium with a resolution that allows us to actually now study the impact, the contribution of the diffuse gas with respect to the cold, clumpy gas associated with star formation, and allowing to answer actually those fundamental questions I phrased before, is how and where the energy is dissipated in such a system. And the bottom line, I won't enter into the details, but the bottom line is that when you look at a galaxy like that, what you're looking at here is the dust emission, the polycyclic aromatic hydrocarbons. So this is the dust emission associated with the diffuse gas. And those studies, this comes from the FANGS collaboration, the FANGS James Webb collaboration. So this is a big collaboration that observed nearby star-forming galaxies. And they've been using those images to actually statistically infer what is the contribution of the diffuse gas, what is the contribution of the clumpy gas at small-scale structures. And they derived that actually most of the dust emission that you see here, most of the orange emission that you see here is coming from diffuse gas. So it's a game changer because before we were biased with CO observations. We were mapping galaxies, molecular phase of galaxies with CO that trace the cold dense gas. Now we can map those galaxies in the diffuse component, and it is the diffuse component that actually dominates the flux budget of the infrared energy. What is interesting is that, well, the mean column density of the gas is fairly low, the gas that is emitting into those infrared bands. And also, they can statistically infer the distribution, the probability distribution of the density of this gas, and it's log normal. And log normal distribution is what you expect from a turbulent medium. If you shake a box of interstellar medium gas in simulations, you expect a log normal distribution. And this is really tracing the fact that you have a turbulent, energy dissipation. And the log normal distribution, they infer the shape of the probability distribution points to isothermal Mach numbers between 5 and 15. So saying that most of this diffuse gas is actually shock-eating and dissipates mechanical energy in supersonic turbulence, via supersonic turbulence. This is just to show you a spectrum, so a spectrum of an external galaxy. This is just a slide to show you what we've been doing before with Spitzer, and now the quality of the data we have with James Webb. This is a galaxy that we took during the commissioning of the telescope. I just wanted to test the shape of the PSF, this cross shape here that is coming from the detector. So we pointed the detector at this galaxy. This is a Seyfert 2 galaxy, NG66552. So you're dominated by the PSF here showing this cross, but this is not what I want to talk about. This is what we took a spectrum, okay, of that source, and the spectrum is full of H2 lines. H2 and ionized gas lines. Actually, we detected a very high ionization outflow in this source. But here is a very unfair comparison with Spitzer. So you see in black, this is the data we have with MIRI in James Webb. And in red, this is the spectrum we had with Spitzer. This is just to tell you the difference in data quality and spectral resolution we had. It was very difficult to interpret those lines or derive the fluxes. Now we can do that very, very accurately. Another very nice example, I think, of turbulent energy dissipation associated with the phases of galaxy evolution that actually drive the galaxy evolution. So this is, for instance, merging of galaxies. This is this Stephan's quintet system where you have two galaxies merging with each other. This galaxy is actually eating this galaxy at a relative velocity of 1,000 kilometers per second. And what we had discovered with Spitzer 15 years ago is that the intragroup medium, so this is a compact group of galaxies, the intragroup medium was filled with molecular hydrogen. What you see here is the rotational emission from molecular hydrogen that is heated by a giant shock when the galaxies collide. But we didn't have any spatial information. We knew the gas was here, but we didn't know its structure. We know it was there. We know it was very luminous, but no structures. Now with James Webb, this is what we had. You've all seen maybe this image. You see that the gas, now we can study the morphological structures of this gas. And you see that it's very filamentary, clumpy, and James Webb is enabling actually to study how and where the energy is dissipating. Why am I saying that this gas is purely molecular hydrogen? This is the spectrum we had before with Spitzer. You see that again, like the one in the protostellar outflow, this spectrum is dominated by the lines of molecular hydrogen in red. There is very weak dust emission in blue here, very weak continuum, and some ionized gas. Now with James Webb, this is the mirror image that you see here. With James Webb, we can actually the structure of those clouds. And we know from the spectroscopy that the H2 lines are the main contributors of the broadband imaging filters we use to image this galaxy. And here it is the mirror image I made, and in green, sorry, the color code, I should have changed the color code, but the green here emission is associated with that filter at 10 micron, and you see that this H2 line is dominating the contribution of that filter. So usually when we image a galaxy before with that filter, we said, okay, it's dust. It's not the case here. This is pure molecular hydrogen that you see here with very weak dust. What's striking in that system and what's really enabling, James Webb is enabling to actually spatially resolve those substructures is that the cold gas, the cold CO gas that we've mapped with ALMA, so this is some zooms in the structure just for illustration. The cold gas, the CO gas is the red, and the green is the warm H2. Seen with James Webb. So red is ALMA CO, green is warm H2 seen with Spitzer. They are not co-spatial at all. It's the same phase of the gas, it's molecular, but they are not co-spatial. They have very different spatial distributions. And we think it's because of the interaction of the shock interaction of those clouds. Some of those clouds may pre-exist in the system. They may be shocked, and warm H2 may be dragged or heated. We don't really know the process that forms this molecular hydrogen, and this is something that we are investigating. But it's very interesting to see that James Webb now allows to actually pinpoint the structures of these clouds. Those are very recent results that we obtained a couple of weeks ago, actually. This is a mapping of the system. This is a mapping of Stephan's quintets in CO. Now we have the full view of the cold gas. So this is CO, how CO is distributed. You see that again, you see this giant filamentary structure associated with the shock by the collision of the two galaxies. You see that there's a galaxy here. It is a Seyfert galaxy with maybe a jet coming out of this galaxy, so very complex system. But the bottom line is that not only the warm H2 and the cold gas are not co-spatial, but they don't have at all the same kinematics. And this is something that James Webb now allows us to do. We've obtained spectroscopy in a few points in this shock. So those different positions here, I'm showing an example. And this is the spectrum of an H2 line, of two H2 lines, 17 micron and 6 micron. So different level of the rotational lines I was talking about. And so look at the width of the lines, 1,000 kilometers per second. And this is the CO profile taken at the same scales. So a few kiloparsec. You see here the scale, it's very gigantic, okay? So few kiloparsec scale, and the profiles are very different in CO and warm H2. What does this tell us? It tells us first that those structures, the CO structures and the warm H2 structure, they don't have the same origin. Actually, the structure that I showed you before, those tails, those filaments that you see, they have a preferred direction in the system. So it may come from the interaction between the galaxies. And this is very reminiscent to the wind-cloud interactions that the simulations are probing, where clouds see a wind because of the high-speed shock of the collision, the 600 kilometers per second shock I was talking about. And perhaps the cold H2 is actually coming from the warm H2 is coming from the shattering of the clouds because of that interaction. We really don't know. We will study that with the kinematics now with James Webb. So this is the toy model that we put forward in that paper, is that you have a fast shock driven into a multi-phase medium in pre-existing clouds, and you form tiny cloudlets, you form some kind of mist of warm H2 that is also seen in simulations. So the clouds are compressed on a crushing time scale that is equal to the size of the cloud divided by the shock velocity into the cloud, and the flow of hot gas is passing this cloud and forming those structures. So it's reminiscent to what we are seeing in simulations. What's nice is that with James Webb, we can study the kinematics of the different components and trying to actually constrain that scenario. Okay. I'm gonna just briefly touch on how the energy is mixed into the system, because this is a fundamental question. And actually what's remarkable is that when you have an interaction between a hot wind and a cloud, this is what we call the turbulent mixing layer, where you drive a gas from one phase to another, you mix the gas, and you mix it to a layer of gas that is thermally unstable, that cools very efficiently. So that may be a way to form the molecular guard out of this galaxy collision. What's remarkable is that the observations tells us that the power emitted in H2 in Lyman alpha, in the ionized gas, and in the atomic gas are similar. So across a wide range of temperatures, the power radiated is the same. And this is exactly what the models of turbulent dissipation actually predicts. This is a result of a simulation of the energy transfer rate as a function of the temperature. And you see that basically it's almost flat. So you get a constant energy transfer rate, a constant energy dissipation rate as a function of the temperature. And this is now what we are observing in this system. How much time do I have? 5 minutes? Okay. I will finish by saying that well, what can we do now with those lines in terms of energy budgets of galaxies? When we observe a galaxy, even with James Webb, you have a mix. You have a mix of reprocessing of UV and mechanical energy. And so you have surfaces in the gas, shock surfaces and photodissociation region surfaces that pave the beam, your observational beam. Okay, so when you observe a galaxy, you have a mix of those processes. So we've designed a toy model where we actually pave the beam with shocks and UV excitation regions, PDR regions, photodissociation regions, which are blue shifted and red shifted with respect to the systemic velocity of the galaxy. So in your observation beam, you have a given solid angle of shocks and a given solid angle of PDRs. Okay. Of course, you have different ways to pave the beam. Okay, for a same solid angle of shocks and PDR surfaces. You can have larger surfaces or smaller ones. Those are two examples with the same solid angles of emitting regions, but different way to pave those. And our model actually uses grids of models to fit those two parameters. So we are actually fitting those solid angles of shocks and PDR surfaces to try to estimate how much energy is reprocessed in the UV, from the UV to IR, how much energy is reprocessed through shocks. Okay? So what we assume, of course, there are assumptions, and we go into the details in that paper. First of all, the regions, they don't have to overlap. Otherwise, you have opacity problems. So we checked all those hypotheses in one example, in one galaxy. Okay? And what we basically say is that our modeled intensity of a given H2 line, for instance, or atomic line, is a sum over probability distribution of shock velocities and PDR surfaces with different radiation fields. And we also investigate different shapes of those probability distributions, exponential, Gaussians, etc., etc. But basically, your observations is a sum of shock distributions and PDR distributions. From this model, we can derive the kinetic energy that is dissipated through shocks, is just the integral times the integral of the shock velocity distribution V cube, the dissipated power in a shock, multiplied by the density of the medium times the square of the angular distance of the source. Same for the UV reprocessed power. So this is a model that allows us to actually derive the mechanical energy and the radiative energy budgets. We use different grids of models. I won't into the details, different densities, different shock velocities, different radiation fields. Okay. And we fit the different suites of lines. You see that now with James Webb, you have forests of lines. So we fit the suite of lines and with the different parameters that describe those shock distributions. What are the results? We've tested that on one galaxy. This is one example. This is a radio galaxy that emits a lot in H2. So we wanted a clear case to actually test this model. Here are the results. You see here, this is the distance between observation and models, so the quadratic sum in logarithmic space of the distance between the model and the observation. So when you go to high distances, the lines are not fitted well. When you go to low distance, they are fitted very well. Actually, 0.5 dex means that all of the lines are reprocessed, are actually reproduced to a factor smaller than 2. So very nice fit. You see the different suites of lines. So those are the intensities of the different suites of lines in that galaxies. Molecular hydrogen up to here, and atomic lines, C+ and O1 lines. And you see the results of the models tells you that, first of all, the best solution is at very low density. This is very surprising. This is unlike what the previous studies have shown, that the molecular gas lines, like the CO, for instance, coming more for the dense gas. Here, we actually have the best fit for the low density. It fits with this picture I told you before, is that most of the reprocessing of the kinetic energy is done in the diffuse gas. This is the phase that is seeing James Webb. Here I can go to high densities. So this is the gas density from 10 to 10 to the 4 hydrogen atoms per centimeter per cc. And you go when you go to high densities, you see that the lines are not fitted well. It's best at low densities. The important two messages here. The important message is that you see that now we can break up the energy budget. You see that most of the H2 lines are reprocessed by shocks, and that lines, atomic lines of C+, O1, and a non-negligible fraction of the very low excitation H2 lines are coming from the PDRs, are coming from the UV reprocessing. So those lines are essential to constrain those energy budgets. The energy budgets are here. What's remarkable with this model is that the amount of UV luminosity we need to reprocess to reproduce those lines fit exactly the infrared luminosity of the source. In red here, this is the observed infrared luminosity. And here, this is the UV luminosity reprocessed. Each squares here is the luminosity reprocessed derived from the model. So it matches. The infrared luminosity is the reprocessing of the UV in PDRs. In green, this is the mechanical energy budget. And in green here, this is less than 1% of the jet kinetic energy. It means that only a very small fraction of the jet kinetic energy of this AGN needs to be reprocessed in shocks. So you don't need a lot of kinetic energy to actually account for those lines. Most of those lines, they are excited by shocks, but only a tiny fraction of the jet kinetic energy is dissipated in the system. Okay, I'm going to stop here. Well, the cherry on the cake, and I'm stopping here, is that when we wrote that paper, we didn't have any James Webb observations of that galaxy. So we made a prediction. Those are lines observed with Spitzer. So those were the data we had before James Webb observed that galaxy. So we made a prediction, but when the paper was accepted, the James Webb observations came out. The paper showing the James Webb observations came out, and we decided, okay, let's check, okay, the prediction of our observations. And this is the suite of lines. So now you see a very forest of lines that was not observed before. All those transitions here, all those row vibrational transitions, they were not seen with Spitzer before. And you see that it's matching very well. So there's some kind of predictive power. We can predict from this model, we can predict and derive the mechanical energy budget. And this is the nice spectrum of that galaxy published in that paper, Leftley et al. 2024. So we were pretty happy about this. Again, the message is that only the mechanical power you need to account for those lines in only 5 to 10% of the total UV reprocessed luminosity of the sources. It remains to be checked on a larger sample. This is my conclusion. In fact, those are my conclusions. So James Webb is now allowing to do very detailed studies of how much, how and where is the mechanical energy dissipation dumped into a system, whether it is an AGN, whether it is initial stage of star formation. So very detailed studies. This is very essential to constrain actually numerical simulations. In fact, talking about numerical simulations, those numbers, I'm going to show you just to conclude, just what James Webb is also saying on that AGN here. Sorry. Sorry about that. Just wanted to show you what, yeah. Whoops. Well, where is that slide? Yeah. Okay. Here, this is also the same kind of study that has been done in the nearby AGN of Stephan's quintet here. And again, from another James Webb observations, those authors, they derived that only a tiny fraction of the jet kinetic energy is dumped into the ISM. What's spectacular is that you have the jet direction here. It's hitting a cloud, and you see enhanced H2, enhanced velocity dispersion. And from the ratio of the jet power kinetic energy, the distance the energy has to travel to hit the cloud, you derive the fraction of the kinetic energy that is dumped into the ISM. And it's a tiny fraction again. So it fits with our modeling results. It's very small compared to what numerical simulations assume and see when they model the coupling between AGN jets and disk. They say that it's between 25 and 30% of the jet kinetic energy that is injected. So it gives a lot of power to those jets for AGN feedback, but this is not what we see observationally. Okay. I'm finishing here. Thanks very much.
Thanks, Pierre. Thanks for a nice presentation. Beautiful spectra and models. I'm sure there are many questions for Pierre.
Yeah, very nice talk, Pierre. Thanks a lot. I mean, it's an extraordinary mixture of theory, modeling, observations, everything. Now, I have two short questions. You said that the flux of molecular lines that you see is mostly due to the diffuse phase. Not the cold course, but the mass is mostly found in the cold course or in the diffuse phase.
Exactly.
So where is the mass? Also in the flux?
Well, you've got a fraction. It's a small fraction of the mass that is in the diffuse phase.
Okay.
Yeah.
So most of the mass is
most of the mass
course.
Still remains in the very.
And the more general question. So molecular gas is coming utterly from the atomic gas. So is there a possibility to find out the relationship? So you showed the relationship between the diffuse and the cold course. What would be the relationship between the molecular and the atomic phase? How to combine those three to see how the stars are utterly formed? Because they start from atomic, then it goes to the diffuse, and then it goes to the cold course.
Yeah, exactly. Oh. Well, this is, I think, this picture observationally, these pictures can be derived from atomic lines or ionized gas lines. For instance, there have been studies in the framework of the galaxy evolution of the Lyman alpha cooling. The Lyman alpha cooling gives you the cooling rates of the gas that goes from 10 to the 5 Kelvin to a few tens of thousands of kelvins. So you get the link between the cooling rate of the hot gas and the cooling rate of the cold gas. This is how observationally we make those links. And those cooling rates, they kind of match. Okay, they kind of match provided that you have feedback. Okay, you need to inject energy, constantly inject energy in the molecular phase. Otherwise, you would overcool. This is the famous overcool problem. So this is how we link the ionized phase to the cold phase. Yeah.
Other questions?
Thank you very much, Pierre. That was wonderful. So I have two questions. So to follow up on Nikos's question, so there are various channels to form molecular hydrogen, and in particular, one involves dust or PAHs, I guess, and the others are just pure gas phase involving, I remember, H2 plus, H minus, and you showed a couple of others. Do you think it would be possible now or in the future to find out in which regions, whether dust is their dominant phase to form molecular hydrogen?
Well, this is very hard to do, first of all. The three-body reaction to form H2 that you talked about in the gas phase, it really happens in a very dense.
Yes, but besides the three-body reactions, there are other reactions involving H minus and H2 plus, and the ion molecule reactions are faster in less dense regions.
Yeah. So in fact, in clouds, it's very hard to trace the excitation that is linked with the process of H2 formation. In models, we have some assumptions, but because you're dominated by collisions, by UV pumping, you're dominated by those processes. So you need to find environments, very dark clouds maybe, or you need to find very specific environments to trace the energy, the excitation of H2 that is linked with its formation process. This is very tricky. Okay, there have been a few attempts in dark clouds, not with James Webb yet, but we are thinking about it. Yeah, but it's a very tricky question.
So my second question, at the very beginning, you showed a circumstellar region where we could not see the disk, but we saw the jets, and you saw molecular hydrogen.
Yeah.
So do I understand correctly that this molecular hydrogen is being pushed by the jet, that it's really outside? Or was it, it's not formed in the jet, or is it brought from the center by the jet outside? I'm not sure I understand what's going on.
Well, it's still an open question. I think. I'm not an expert on protostellar jets. Perhaps they are in the room, but in fact, what is sure is that the jet is mostly molecular. Okay, this is the main carrier of the gas is molecular, and in fact, when the jet is hitting the cloud, you form those bow shocks. So gas can reform, H2 can reform in the post-shock gas in those phases. A fraction of the gas may also be entrained and cools as it's flowing out of, so I think they are both. I don't think there is a clear-cut answer whether most of the mass is actually reformed as gas is flowing out and cools, or whether it is mostly untrained. I would say it's mostly actually cooling as it flows and cooling very efficiently where you have bow shocks. Yeah.
Okay, thank you.
Because same for AGN jets maybe, or galactic outflows.
Thank you, Pierre. I have two questions. One is about the Stefan Quintet observation of the H2 intragroup emission. Do you have dust there? Do you see dust?
Yeah, we see that. We see dust. We see very weak emission. This is, I didn't have time to actually enter into the details, but we see very weak dust emission, and this dust has to be there for H2 to form. Okay, so the dust has to survive the very high speed collisions, and this is why we say, okay, this is the very fast shock hitting a multi-phase medium, and the shock driven into the clouds, they are lower velocity than the high speed shocks in the diffuse gas. Otherwise, the dust would be sputtered and destroyed. So we see weak dust, we see weak pHs, okay? We see very weak continuum. You can barely see it here, but I don't have it here, but we also see far infrared continuum from the Spire, from the Herschel observations, and we see dust in the shock. So dust is there, but it's not heated. It's not seen, it's not shining because the star formation is very low, because you don't have any stars almost forming. You have a few stars forming in the system, but very low. The star formation rate, the mass of the gas in that system, you have as much molecular gas in between those galaxies as we have in our own Milky Way, 5 billion solar masses of warm H2, but the star formation rate is only 0.07. So there's a lot of molecular gas, but not forming stars in that system. This is why dust is here, but is not heated by UV. So the H2 over dust emission is very high. This is why we use that ratio to actually probe galaxies that are mostly dominated by phases of kinetic energy dissipation.
And why the star formation rate is so low compared to a typical Milky Way?
We don't know. Is it turbulence? Is it because you have those interactions between the hot gas flow and the gas? We don't know why those clouds, they are not forming stars. We suspect it's because of turbulence. You've seen those H2 velocity profiles. They're quite spectacular. Usually we observe the H2 line width of, I don't know, let's say than 100 kilometers per second in galaxies. Here we observe thousands. We don't know whether you have multiple velocity components. It's complex, but something is going on with this gas. Yeah.
Okay. Here's my second question. With this James Webb data on H2 gas, you learned something new about the CO luminosity over H2 mass?
Sorry?
Do we learn something new about the CO luminosity over H2 mass? That's often used for high redshift galaxies.
Yeah, the dark H2, the dark CO gas. Yeah. Yeah, there have been a few papers. I didn't want to do a review here, but rather than focus on a few results, but there have been some first papers about dark CO gas and James Webb observations. Those are the studies done by Soumaden and Vianney-Le Bouteiller. So they've observed molecular hydrogen in very low metallicity galaxies, where you have those H2 over CO ratios that are very peculiar, and they derived from the modeling, they derived fraction of the gas that is dark in CO, that you don't see in CO, but you see it in H2. So indeed, James Webb, I think, will open new perspectives in that. Yeah.
Okay, let's thanks Pierre again.
Thank you.
Thank you.